I'm excited to be able to speak here. I know in this room there are many experts in AI and machine learning. I myself come more from operations research background, but I hope there are many opportunities to sort of collaborate in the future. And so for this talk, I'm trying to not make it technically very deep, but instead I try to be broader so that I can maximize the chance of touching things that you are interested in. Okay? And this is joint work with two great colleagues at Columbia IUR, Adam and Garut, and also four excellent PhD students, Tuan Yu Yibo, who's graduating and going to join Meta, Hao Fan, who's also graduating and going to join Morgan Stanley, and then Yang Fan, who's now a postdoc at Harvard. First of all, yeah, as I said, I come from operations research, and in OR, we care about decision making. These decisions could come from, for example, industrial problems where you want to maximize your revenue. In finance, you want to optimize your portfolio, and in nonprofit, maybe you are more concerned about risk control. As we all know, with the growth of data, which I know in this room many of you are at the forefront of this. A lot of the activities in OR is about the integration of data or AI into decision-making tools like optimization. Okay? Now, before I maybe go ahead to talk about some details, I just want to briefly maybe discuss some examples of how this kind of integration between data and optimization can be achieved in practice. So this is actually a joint project between Columbia IUR and Columbia Civil Engineering with the New York City Fire Department. So the New York City Fire Department oversights basically the 911 emergency medical service system in New York City. And so what happened perhaps 2 to 3 years ago, actually more than that, maybe 3 to 4 years ago during the peak COVID time, there was a crisis in New York City where some of the hospitals were overwhelmed. Maybe some of you have read the news. And so this map is actually showing the New York City. And the circles on these maps correspond to the 65 hospitals in New York City, where a bigger circle means essentially a more congested hospital. So you can see that, actually the sort of rectangular tube in the middle is Manhattan, which is the business area of New York City. And you can see that the bigger circles, which are red in colors, are in the outer boroughs, in the outer part of the city. And this is actually happening because there was a mismatch between demand and supply during the COVID time. Because people work from home, those who used to go to work now in the outer boroughs area. And so because New York City used a policy of sending patients to the closest hospitals, that actually exacerbates the overwhelming congestion of some of the hospitals in the outer area. And so Columbia, teaming up with the FDNY, try to find some methodology that can prevent this overwhelming of hospitals to occur before it actually happens. Okay? So by perhaps smartly assigning patients to hospitals, we can avoid these congestions in hospitals before they happen. And so what we came up at the end is essentially a data-driven optimization program that constructs the 911 scene to hospital assignments. And so at the beginning of each day, what we did is to solve a constraint optimization problem where we try to minimize the system-wide travel time, but subject to the constraint that the hospital capacity has to be respected. Okay. So in this way, instead of sending patients to the closest hospitals, because of the constraints there, we would, the optimization program would automatically assign a hospital that is farther away but at the same time, the hospitals might be less congested. And this is a data-driven optimization because in order to make it work, you need to feed several predictors from the data, including the spatial distribution of the frequency of 911 calls, hospital capacity data, and also you need travel time predictors throughout the city. Yeah, so at the end, this approach passed in New York City, and it was implemented twice during the COVID time when the wave of COVID cases arise. And so when the ambulance crew, when they send patients, pick up a patients, they will actually see in the ambulance, there's this load balancing recommendations built by FDNY in Columbia. Yeah, so I just want to briefly say that this kind of data optimization integration happens all over the places, and typically there are 4 elements in this framework. So of course, when you solve optimization, you need the objective function. And then you might have constraints, and typically you would also have some randomness in your system. And so for example, in the load balancing example, the objective could be the overall travel time. Whereas in Newspander problem, for those of you who might not have heard this term, Newspander problem is a standard retailer profit maximization problem. So in this problem, the objective is to maximize the profit. And then the constraints, in the load balancing problem, it could be the hospital capacity constraint, but in Newspander problem is the inventory capacity. And then the randomness in the load balancing problem would be the travel time and the incident counts spatially. And then in the Newspander problem, it could be the demand of different products. Okay. Now, I also want to mention that sometimes we also have contextual information. So in machine learning, this is really this is very familiar in supervised learning, where you might have covariate or contextual information. So similarly in optimization, perhaps the setup is before you try to optimize, you can obtain this kind of information, such as weather, the season, location, etc. And the randomness is conditional on this covariate. Okay, so so in this talk, I will focus mainly on 3 questions. And as I said, I'm not going to dive into the technical details, but rather I just want to give you a sense or a taste of what have been done in the past and what we are currently doing. So the first question is, when you try to integrate data into optimization, how do you handle the uncertainty coming from the data? Okay. So in the optimization literature, there are 2 main paradigms. The first paradigm is empirical optimization, which is probably familiar to most of you. This is essentially empirical risk minimization. You simply replace the unknown expectation with the empirical average. But in optimization, there's also this other very popular paradigm called robust optimization, which is a worst case approach where because you don't know something, so you assume it's the worst, and then you try to make a decision on the worst case scenario. Yeah, so I'm going to talk about some developments that try to justify or compare these 2 approaches. And ultimately, I also want to talk about like a new view on these approaches that has to do with how you hedge the complexity of your function class. Okay, so this is the first question. And then the second question I'm going to try to discuss is, instead of saying integrating data with optimization, it's probably more accurate to say that you first have to build a model coming out from the data, especially if you are in a contextual situation, a supervised learning situation. So you first build a model, and then you integrate into the optimizer. Okay? Now the question is, since you have this optimization, downstream optimization in your mind, do you actually train your model just like standard machine learning recommendations, or do you want to take into account this goal-driven optimization in your training process? Okay. So again, I think one dichotomy of this is perhaps you can think of this as you first estimate or predict, and then you optimize, versus you integrate the optimization and the prediction together. Okay. Yeah, so I'm going to discuss this, and also something about like a theoretical framework that I call stochastic dominance on the regret that comes out from this discussion. Okay, and then the third question is, just like in machine learning, we do model selection all the time, or hyperparameter tuning. So here, in this data optimization integration, we also have a problem of how do you select or evaluate your decision. Okay. So perhaps highlight is something that we are currently working on. Is instead of using a hierarchy information criterion, AIC, we try to build something that is more relevant for optimization, which we call optimizers information, OIC. Okay, so yeah, so for the rest of this talk, I'm basically going to focus on these three questions. And before I go ahead on the first question, first, maybe I'll just introduce some notations. I'm going to use the lowercase letter x as your decision. And then h is a known cause function. So in machine learning, you can think of this as just the loss function. But in OR, h could be a whole variety of objectives coming from the downstream task. And then P is the distribution on the randomness that I call Kasi. And the setup is you don't really know what is P, but instead you collect data, let's say Kasi1 up to Kasi. And in fact, typically the problem is much more complicated. You could have contextual optimization, which means given the covariate x, I now want to optimize this expected conditional expectation. And so instead of just finding a single x as your decision, now x is a policy. It depends on your context. And then P here now would denote the conditional distribution of Kasi given the covariate z. And then when you collect data, you might have label the data Z1, Kasi1 up to Zn, Kasi. And then in addition, you could also have constraints. So here, I'm just simply putting deterministic constraints. So think of G as some deterministic function. And I need to make sure that G as a function of the decision has to satisfy this inequality for every covariate. In general, you could also have random constraints. But this would goes to so-called trans-constraint program or expectation constraint program, which I'm happy to talk offline, but it's not going to be in this talk. Okay, so in fact, for the purpose of this talk, I'm just going to go back to this very basic setup. I don't want to introduce the complications because most of the concepts would already appear in the most basic setup. Okay, now for the first question that I introduced before, which optimization under uncertainty approach should we use when you have data? So as I said, empirical optimization simply just means you replace the unknown expectation by a sample average. So this is empirical risk minimization. Now, for robust optimization, what it means is if you have an optimization program where you have some parameters that is unknown. What you do is you try to minimize the worst case. Okay, the worst case is captured by the maximization in the inner operator of this program. And this worst case is over a set, typically called uncertainty set or ambiguity set. Intuitively, what you do is you try to find an ambiguity set that contains the ground truth with some confidence. This may or may not work. Okay? So I just want to caution that. I'm going to discuss more in the next slide. But if you have a stochastic problem, in fact, instead of using robust optimization, typically you would use distributionally robust optimization. This means that the uncertain parameter in your optimization program is itself a probability distribution. It is the probability distribution that controls the randomness that is unknown in this problem. Okay, so correspondingly, the ambiguity set is in the space of distributions. Now, if I drill further into this distributionally robust optimization, DRO, in fact, you could see that the only part that you need the data is U. The ambiguity set contains all the information from the data. Nowhere else in this min-max problem needs you to work with data. Okay? So in other words, the choice of U is critical if you want to have some meaningful property out of this program. Okay? Now, in the literature, there are two major ways to specify this ambiguity set U. One is to set it as some neighborhood for surrounding some baseline distribution, P hat. So for example, P hat here could be just the empirical distribution. And then the D here denotes some statistical distance, like Kubert-Leiber distance, phi divergence, Wasserstein. And then, the ambiguity set basically says, this Q cannot be too far away from the baseline. The other way to specify the ambiguity set is to use partial information about the distribution, like moments, supports, the marginal distribution, or you just specify that your distribution is convex in terms of the density. Yeah, so all these are very well documented in the literature. The question is, what does all this buy you, right? So if you look at the literature on DRO, there are basically two dominating views. One is what I call a worst case guarantee. This is really the classical view. This is where the notion of robustness comes in. So basically, if you choose this ambiguity set U as a confidence region for your unknown distribution, then there's a almost automatic guarantee that once you solve this problem, you obtain this XDRO, which is your DRO solution. The true performance of this solution will be upper bounded by the optimal value, basically the output of this program. And this, the proof of this is really just one line. So it comes from the fact that you are doing a worst case.
May I ask
yes.
Here? So in your case, in your case, do you assume that Casey is very general form? You don't focus on, or you don't consider some like a classification problem, and you don't assume H is like a differentiable.
Yeah. No. Yeah. So this result has no assumption.
Yeah, because we had a paper in ESMA 2018. It proves that if it's classification, then if H is the 0-1 loss, then the DRO just doesn't work.
What does it mean by doesn't work?
Like the mechanization just it will not do anything. It's very counter-effective.
Yeah.
But if it's the square loss or if it's not a classification, then maybe it's fine. Because in classification, both the decision, the cassette, and the loss function is not continuous.
Yeah, well, if I understand you correctly, in fact, I have never said that this is a good guarantee.
Okay,
this guarantee can be extremely conservative.
Okay, thank you.
In fact, if you just take U to be the entire set of distribution, then it's doing nothing.
Okay,
it's a trivial.
Yeah, because from my own experience, if it's classification, even if I use like the cross entropy loss or the square loss, the performance is not very good. It's maybe too robust and so not very effective.
Yeah.
Oh, okay, but
sorry, go ahead.
But I feel if it's a regression or maybe other problem, then this will be a good choice.
Yeah, so I think the next few slides may be related to
okay, thank you.
So what I want to say about this guarantee is this is a very classical guarantee. It comes decades ago. And in fact, in my mind, this guarantee is the most useful if you don't have much data. In fact, for example, if you have multi-sources of data, you don't know the correlation among the data, but you might have the marginal information, then you can specify an ambiguity set that is the marginal type, but you lack the correlation free. So that's one way to get some upper bound for your performance metric. Or maybe you are encountering a tail estimation situation where you just don't have too much data in the extremes. And so in this case, you can impose some shape information as a prior, and the DRO would give you some upper bound that at least it works, but it might be conservative. Yeah, so in fact, the more contemporary approach is to think of DRO as some regularization. In particular, this is known as variance or variability regularization. So what it means is if you pick this ambiguity set U as a neighborhood ball surrounding the empirical distribution, then turns out the worst case objective value can be viewed as the objective value that you obtain from your empirical optimization plus some penalty term. And that penalty term has to do with the variability of the cost function. So for instance, if you have a Quebec library or cross entropy, you would have the standard deviation of the cost function in the penalty. And then if you what's the sign, then you visit the Lipschitz norm, the cost function. So, there are several uses of this result, but one implication of this is that you can try to work out the generalization bound for DRO, and because of this regularization effect, it turns out that it has some benefit over empirical optimization when the cost function has a small variance. So that's one insight coming from working out the generalization bound using this approximation. Now, going back to your question, the thing is, this sort of two established views. One of them, as I mentioned, is actually more useful when you think about a situation where you don't have much data. And then the other one has to do with the variance being low, which may or may not hold in the problem. So recently we have tried to come up with kind of a new view of how DRO can potentially outperform yield or help yield. So first of all, if you look at the regret, or some people would call it optimality gap, some people call it excess risk, but basically it means the true performance of your obtained solution that I call X hat minus the true performance of the Oracle solution X hat. So if you look at the generalization bounds for either empirical optimization or the DRO, they would depend on some sort of complexity in some way. So for instance, in empirical optimization, you need to have the complexity of the cost function class. You may be able to refine this bound. Maybe you have some localization that you can make it better, but still it depends in some. And for DRO, if I use the regularization view, still, because it's actually a regularized yield, you will still have the complexity on the function. Now, on the other hand, if I try to use the worst case view, it turns out that you can actually remove the complexity of the cost function class. But the price to pay is you would have some complexity dependence on the distribution itself. So the way to think about it is if you try to decompose, so there's a standard way that you can decompose the optimality gap into several pieces. Usually, when you try to analyze empirical optimization, you would have a piece that looks like the true performance at the yield solution minus the empirical performance of the yield solution. And this is where you typically use uniform bound and you have the complexity dependence. Turns out if you do DRO, this empirical performance becomes the worst case performance. And this first difference becomes negligible. But the price to pay is when you come down to, there's another piece in the optimality gap, which depends only on the Oracle optimal solution. That piece depends a lot on how you specify your ambiguity set and the size of the ambiguity set. And typically, if you want the ambiguity set to contain the ground truth distribution, then the size of the ambiguity set is scaled up in the dimension capital D here. So that's why the n to the power 1 over d is, for example. This is the case in, for example, Wasserstein. So that's why I say that, it seems like all the approaches previously, in either case, either the complexity of the function class or the complexity of the distribution shows. So I'm not going to claim that we can try to remove all this, but if you are going to, try to leverage some distribution structure, then there's a way that you can distort the dependence on this complexity. So basically, what we do is a very simple approach. We call it parametric DRO, where if you look at the generalization bound of this, it doesn't have the dependence on the function class H. It also doesn't have the dependence on the capital D, but instead, it has a model misspecification price in the bound. So what we do in this approach is you simply fit the best parametric distribution on your data, and then you robustify by imposing a ambiguity set surrounding. So if you do this, then the parametric approximation would replace the complexity of H and the capital D by now is the complexity of your parametric class. So the theta space, theta is the parameter. And then the DRO serves as a way to control this misspecification. Yeah, so this is like one basic theorem in our paper. So suppose you can pick parametric distribution class P theta, such that the distance between your true distribution P and basically the best your theta distribution P hat in this class, if it satisfy this error bound, where the first term E is the model misspecification error, and then the second term is the statistical error coming from your theta. So typically it depends on the complexity of your parameter space theta, and then n to the alpha, where alpha depends on your distance choice. So for instance, if you have you use a Gaussian mixture, this statistical fitting error, you can work out alpha is one half, and then the complexity of theta is the number of Gaussian mixtures times the dimension. So if you have this assumption, then turns out that the generalization error on the regret of the PDRO will be simply bounded by the variability measure, Vx star, times this delta, which is the bound on the distance between P and P. So it's a very simple bound at the end. Now, if I try to apply this bound, then our claim is, if you look at basically the table, the left-hand side column is the complexity result that I showed 2 slides earlier. Now, if you use the parametric DRO, then you get a generalization bound that coming from the field. So the variability measure Vx star times this delta thing. Yeah, so it does remove complexity of H and D, replaced by complexity of theta. And suppose you only fit the parametric distribution, but not using the DRO. So you have something like a parametric EO. Then basically the misspecification error E would be amplified by this M. M is a uniform bound on the cost function. So looking at this comparison, you can see that the DRO, this parametric DRO will be preferred if the distribution class is simpler than the function class, because in that case, basically the misspecification error E is small, and then complexity of theta is smaller than the complexity of H, and so overall PDRO will be superior. I also want to mention, actually all these results you can generalize to distribution shift setting. In a sense, distribution shift is like misspecification error. So just like how the PDRO reduced the sensitivity to misspecification error over the parametric EO, it's the same thing happens, that the distribution shift impact is going to be de-amplified when you use the PDRO. I also want to mention, it also generalized to contextual optimization, where now you have a context before you do the optimization. And in fact, in that case, you simply cannot use empirical optimization because it easily overfit. I will have a slide on that later.
I couldn't really understand the distribution shift part. Would you say that again?
Yeah, so distribution shift means when you, so you have past data, you use it to come up with a solution. And then when you apply the solution, the data comes from a different distribution.
Without taking into account any information from about the domain.
Yes. Yes.
I don't understand the last point, that contextual optimization. It is arguably necessary to use parametric approach because there's like not enough data for all those contexts. Is that the point of?
Yeah. So for this question, I can go back to this slide. So when I say contextual optimization, I mean that first give me the Z, and I have to solve for the X. So in that case, suppose I want to use empirical optimization here. Okay, so I have my data set is Z1 C1 up to Zn Cn. So what I would perhaps naively do is to somehow replace this thing. In fact, this is, by the way, this is actually when you actually do the optimization, it's not just one optimization. For each Z, you have a different optimization. But if I use the EO approach, I would just simply set the average on H of X of Cassie, and then
in the case of context, you have to find a decision policy as yours, right? So it needs to depend on Z, I guess, X, ideally.
Yeah, so let's say, let me do it this way. So suppose the function, the policy is free. So you can pick any function here. So X bracket is any function. Then suppose I simply take, so this Z and C becomes a ZI and C, and then you end an average of this. Then you would just simply take X of ZI as the best solution for CI. And then for all the other, and suppose the covariance is continuous, then for all the other X of Z where Z has not been observed before, you really don't have any optimizer there. So essentially the EO will give you a solution, a policy class that looks like it works perfectly for any historical ZI. And then for all the unobserved Z, it's doing nothing for you.
Okay, but I mean, if you parameterize it, so it depends on Z, and you can make assumptions that it's still tractable in some certain cases, right?
Yes. So if you make a assumption on the class of X, it's called the end-to-end approach. The problem with that approach is you cannot satisfy the constraint. Your constraint has to satisfy for every Z, and typically, it's not easy to train to find a class that easily satisfies.
I see. Thanks.
I didn't fully understand the parametric EO part, because to me, EO, if you don't consider it, you don't want it to be DRO, then why you want to estimate P and use P hat? Because EO itself is discriminative. There is no motivation to model the data generation distribution.
Yeah. So exactly. So in fact, if I go back here,
this one parametric EO part.
Yeah. So when I say parametric EO, it's actually very simple. You just feed your data into some parametric distribution, and then I pretend that this distribution is the ground truth, and I solve the optimization problem.
Okay, because I thought that if it's not a DRO, after I estimate the P and obtain P hat, I have it's not very, say, if it's generative learning, then I already know the data is approximately generated from P hat, right? But I assume you are talking about the EO to be the descriptive learning, the empirical risk minimization. So maybe I have no easier way to really incorporate the information in P hat into empirical risk minimization.
Yeah, so maybe I shouldn't use the word E, just parametric optimization, which is legitimate. At least what it says is a trade-off, right? So if you take a non-parametric approach, then you might encounter the complexity of H, right?
If I assume the hypothesis H is some neural network or is a linear model, it's still a parametric approach. Just we don't assume the distribution of the data to be some parametric model. Maybe it's different. Okay,
well, yeah. So in fact, you can think of neural network as one example. In that case, the complexity of theta would actually be huge.
Yeah.
But then the E would perhaps be small.
Because this is the first time I saw this some complexity plus M times E. There is some additional like a bias term that does not converge to zero.
Yeah.
Okay, so thank you.
Yeah, exactly. Yeah, so in fact, this is also the first time we use this. And I think the intuition is we try to leverage our guess or our knowledge that the E is small. If the E is big, that means you are fitting basically a wrong model, and this is just bad. So it has to be the case that your model fee is pretty good. In that case, the E is small, And then turns out the DRO actually buys you even more. It reduced the effect from the misspecification.
Oh, I see. Because it's small, so parametric approach really is helpful. It will not be harmful.
Yeah.
It's fine. I think.
I mean, another viewpoint is all these complexity results are worst cases. Basically, these complexity bounds assume that the distribution is free. You can choose. We are basically doing the other way. Try to leverage some structure about the distribution, and this structural assumption is inside this. Okay, any more questions? I do have 2 more questions I want to discuss. I can do it quickly.
We have plenty of time.
Okay. Yeah, in fact, the second question is also related to your question. So suppose I feed data into some model. The question is whether I should just train this model using off-the-shelf package, or should I take into account the downstream optimization? And just to clarify, what are these? What do I mean by sort of this predict and optimize or estimate and optimize versus the integrated approach? This is kind of the protocol in these procedures. And first of all, as I said before, and related to your question, in contextual optimization, I cannot really use EO, at least not in the standard way, because it basically would give me a policy X that does not work for any unobserved covariance. So let me use a parametric approach. Again, it means I feed P into some family P data. And in order to concretely introduce this approach, first, let me define what I call oracle problem. Oracle problem means, for this parametric model, suppose I'm given this data as the parameter. I'm going to plug into the optimization problem, pretending that P data is the truth. And then that will give me a solution, X data. So this is what I call oracle. Now, when I say estimate and optimize, that means in the first step, I simply just feed, estimate this parameter data from some standard approach, maximum likelihood. This has nothing to do with the optimization that I have in mind. And then once you have this theta obtained from your step 1, your step 2 is plug this data into your oracle problem. So that gives me XETO, estimate and optimize. Now, the integrated approach, what I call integrated estimation optimization, IEO, means the following. You basically solve the empirical optimization, but using the oracle problem, X data, in your solution, in your decision. So you optimize the data there. And then step 2 is the same as the step 2 before in ETO. Okay, so when you think about this, at least, intuitively, IEO should be the better approach. If your ultimate objective is the objective function of your downstream optimization problem, IEO should be the best. It's basically the empirical optimization that accounts for this downstream optimization. Now, and this is indeed the common belief in the literature. People think that IEO is preferred. It's just that it has one catch. It's very hard to implement. Because, first of all, you need to parameterize this data, X data. And then it's not even clear that the optimization problem is easy to solve. Even if the original objective H is nice. And you cannot use any off-the-shelf machine learning package if you use IU.
Yeah.
Yes.
Sorry, I didn't get something there in your description of H of
Yeah.
X theta, but actually you didn't optimize X rate, right? So it's kind of so actually what does that mean? R min over, because in the ETO it's kind of clear that you are first estimating theta and then plugging that in to your original problem, right?
Yeah.
But here you want to do it somehow together.
Yes.
And so you have to also, in the step one, also do two optimizations kind of, or something like that.
Yeah, so step one, so in this objective, so first of all, this objective function is used to get your best data. Right? And this objective function has two things. One is there's an empirical estimate of your downstream optimization objective. So that's the summation of the H, right?
Yes.
But inside the H, there's a decision X,
Okay.
which is parameterized by theta.
I see inside.
Yeah.
You can say xt theta as the R min of that other problem.
That's right. That's right. Yeah. In this way, it is integrated.
Okay.
But the thing is still the conversation of P,
Yes.
not X. So it's very difficult. Okay. Yeah.
Yeah. So unless you specify the class, the parametric class of X theta, by using some other means. Suppose you say X theta is some neural network or some linear function of theta. Otherwise, typically it is very hard to get down this X theta because it's itself an optimization problem. Exactly. And then going back to your question earlier, some people actually try to do this parameterization on X directly. Again, as I said, this is the end-to-end approach. It has been considered. The drawback of this is when it comes down to constraints, it's very hard. Yeah, okay, so what we try to understand is, at least we have a result that tries to understand, is it really worthwhile to use the integrated approach? And here's sort of the message is, suppose you look at a large sample regime, and you look at the regret. Okay? Again, the regret means true performance of your ETO or IEO solution versus the Oracle performance. Now, if your model is well specified, so that means you find the right class. The P data is the right class of distributions. Then turns out ETO is better. And it's better in the sense that if I look at the regret in the large sample, by the way, the regret is a random variable because the regret depends on your obtained data-driven solution, which has the randomness coming from the data. So when we compare two regrets or two random variables, one way to do it is to use stochastic ordering or stochastic dominance. And so the result basically is that, under some optimality conditions of your optimization problem, the asymptotic regret of ETO is always better than the asymptotic regret of IEO in terms of stochastic dominance. Yeah, so there are a lot of notations here, but perhaps I would just mention that, first of all, this capital R means the regret of, there's actually a typo, it should be a X. The regret of the ETO solution, in general, under optimality conditions, is scaled with 1/n. So it's kind of in the fast way regime. And it converges, if you scale up by n, then it converges to some random variable, which I call GETO. And similarly for IEO, and in fact, I can also put EO into this comparison, even though yield, as I said, in the contextual case, it just breaks down. But nonetheless, this result, the implication is just like the first part of the talk. If you actually have a good model, then in fact, it's not necessary to use IE. Meaning that if your model with execution error is very small, this result roughly says that ETO is actually preferred. Yeah, so again, you can extend all these results to constraint case and contextual case. I also skip all the proofs in this talk, but it has to do with manipulating some Gaussian sum of squares, and which is important. Okay, so I think I'll just use maybe 5 more minutes to just briefly go over the third question. So this question is, instead of doing model selection in machine learning, now we have an optimization, a data-driven optimization, and we have different ways to find this data-driven solution. So the question is, how do we evaluate and select the best decision in practice? So, so once again, let me assume that I use some parametric approach. So the solution X depends on this data. This data can come from IEO, ETO, whatever. Okay. So for given problem instance, even though I have all these insights previously, those theoretical results are not really instance by instance. So if I'm given a particular objective function and data, it could very well be the case that one is better than the others. And the question is how to select. And so there are actually a bunch of criterion you could use. One simple criterion is you simply look at the expected regret. Or in other words, the expected objective performance. And I'm sure people in this room knows very well that there's this optimistic bias or overfitting that occurs. So suppose you obtain this data-driven solution and you reuse the data to evaluate that solution, it's going to give you a bias. And then the question is how to remove that bias. And there are a few approaches in the literature. You can use cross-validation. Typically, the leave one out cross-validation is the gold standard. The problem is it's expensive. So some people use K-fold cross-validation. So instead of leave one out, you leave one batch out. And then you evaluate on the remaining data. And you do it K times. And I'm not sure if this is well known or not, but in fact, K-fold cross-validation typically is not better than the naive evaluation. Just simply reuse the data used to obtain your solution in your evaluation. The naive evaluator usually beats K-fold CB because K-fold CB, when you leave one batch out, that batch is significant. So it turns out it affects, it actually has significant negative impact on the evaluation.
I didn't really get that point, because if we take a model complexity on the horizontal axis, then naive error just monotonically weighs down. But cross-validation error usually has a bottom. Like AIC.
Yeah. Yeah.
The behavior is completely different in practice.
Yeah. So actually, this is a very good question because I should clarify. So in terms of the evaluation accuracy, K-fold, well, we find that K-fold is not really better than naive evaluation. But in terms of selection, K-fold could be better because the selection process, you just have to make sure the trend is accurate. Right? You don't need to ensure the evaluation value is accurate.
So accuracy basically means the error is something like 1 over square root of n or something.
Even in the case of cross-validation, it should be almost unbiased estimator of the true risk.
Yeah, so quality of evaluation means, suppose I have the true performance of your solution. I simply look at the difference between your evaluation and this true performance, which typically you don't know, but in experiments you can, or in theory you can work it out.
So in that case, like leave one out cross-validation is an almost unbiased estimate of the true risk. Right?
Yes.
And K4 is a bit biased, but it has much smaller variance. So in practice, we are recommended to use K4 cross-validation or just K. It's not. It's just validation data. Right? We just split the data into the training part and validation part, and use the validation part to evaluate the performance. This is a kind of gold standard that everybody does in machine learning. So it's not that clear to me why this is not better than the naive estimator.
Yeah, so we have in fact at the end I have a citation of a paper that would love to have your feedback, because again I don't know if this is something that is known or not, but at least that's our results. That says basically the K4 CV, even in terms of the removing the 1/n bias, it does not really work that way. It does not reduce that 1/n bias. If your solution, well, it depends on what solution you are going to use at the end. If you use the entire data set as your to train your ultimate solution, and then you use the K4 to try to evaluate that solution, then there's a gap in terms of evaluation.
Leave one out cross-validation gives an unbiased estimate of the risk for n-1 training data. And K4 cross-validation does similar thing for like 80% of training data, but K-1.
Yeah, as you mentioned, the purpose is a bit different. But the purpose is a bit different. We are talking about evaluating on the validation data because we want to do some hyperparameter tuning. But he is really talking about evaluating on the test data. Suppose that we are doing some research project, and the conclusion is that if we can achieve some performance on the test data, then we will get the fund, or the company will mass product this one. So what matters is really that estimated accuracy, not the hyperparameter selected based on the estimated accuracy. I think this is really a big difference.
But in that case, just the empirical error is a good approximator to the test error.
Maybe he mentioned that for K4 the CV, the estimated accuracy will be much smaller than the true test accuracy. Even so, this is okay for selection.
Yeah, because the relative trend is kept in some way, but the absolute number is not reliable.
Yeah, for example, I can give you some concrete example. You get the true test accuracy and you divide it by 2. Then the estimated test accuracy is not accurate at all. But if you use this to select a hyperparameter, it's fine because it has a system dependency. Right? I think this was the point.
So even as an estimator of the true test accuracy, why is K4 cross-validation poor?
Because you use much less training data. I guess.
If K is okay, if K is 2, it's only
yeah. Because usually you assume that K is small. Otherwise, it's very similar to leave an order.
Yeah, maybe I should say. So I'm claiming this in terms of asymptotic result. So when you say 80% of the data, maybe the number of data is 1 million. So you lose 20% of 1 million, which is still a big number.
Yeah, usually when we talk K4, the K is smaller than 10, right? So you lose a lot of training data. That's why it is less accurate than leave out and even the somehow the naive. Okay.
Thank you.
Yeah, thank you. Well, you answer much better than me. But yeah, so bottom line is, at least in our paper, we were able to show in terms of evaluation is not better, but we have not gone up to the hyperparameter tuning of the selection. I think it's actually an open question of general objective function that we're talking about. Yeah, so in the literature, we also know about some approximate leaf-one-out method. Basically, leaf-one-out cross-validation is too expensive. So there's a way to at least analytically approximate part of it. So that's the leaf-one-out. And then lastly, AIC, which is very well known in classical statistics, and is tied basically to log likelihood function. Yeah, so we sort of look at what we call OIC, basically as a generalization for AIC, in the sense that if the objective function is the log likelihood, you reduce back to AIC. But if the objective function is general H, then it takes a form that looks like this. There's a lot of notations, but at the end, maybe I just give the high level understanding is, you have the empirical evaluator, which is your first term. And then the second term is sort of like a debiasing term. In AIC, this is just the dimension divided by. But now, if you have a general objective function H, in general, it sort of looks like an inner product of two terms. The first term is like the gradient of H with respect to theta. And then the second term is the influence function of theta with respect to the underlying distribution. Influence function, you can think of it as, in general, if you have a statistical functional, basically a function on distribution, and you want to take the derivative with respect to a distribution, then it becomes the influence function. It is the notion of derivative with respect to probability distribution. Yeah, so you can work out this formula for different cases, IEO, ETO, end-to-end, whatever, and there are explicit formulas for OIC. But bottom line is, if you use this, then it does reduce the bias. So you look at the expectation of this OIC, it's going to be the expected true performance plus an error term that is smaller than 1 over. And maybe this is probably my last slide. So we sort of have a small comparison with existing methods. So if you look at, go down the road, if you try to understand which method is the most computationally intense, E1 now is the most intense. In general, you need to solve the optimization n times. If it's a big optimization problem, it's going to be time. And if you use k-fold, yes, you can reduce the k. Turns out if you do approximate leaf-one-out, sometimes it's 1, but sometimes it's actually depends on whether you use ETO or IEO, one of these data optimization integration. And OIC, just like AIC, is you only need 1 time. The price to pay, though, is OIC is not model-free. You need the influence function. And this is also the same as AIC. Removing bias, OIC, similar to other approach, except the k-fold, as I said, you lose too much data on that. And then we focus on general problems, so constrained problems or more general objective functions. OIC can also work. Explicit bias formula, just like AIC, OIC is an explicit form. Okay, so I think I will end my talk here, and these are some of the references for the. Yeah, so first question is about the DRO and the parametric DRO. It's in these 2 papers. The second part is about the stochastic dominance framework. the other two papers. And then the third part, so about the question of K-fold, how does it compare to naive approach? That's in the last paper. And as you can see, a lot of these are very recent.
Just not technical question. So I'm not familiar with like journals of management science or operation research. So do they have like machine learning papers like this? I would call them machine learning papers.
Yeah, so they recently, so these are general audience papers in OR, and they have areas in the journal. For example, an area could be simulation, another area could be revenue management. So recently, both of these journals create a machine learning area.
I see.
So they wanted to get some share of that.
You should check also these journals.
Well, yes, but well, it's recorded here. But these journals have a long, usually have long cycles than machine.
Any serious questions?
Thank you very much for the interesting talk. I have a question about the OIC, or maybe the slide before the slides. Yes, it looks like OIC outperforms the other implementation method. In your talk, you mentioned maybe the only price we need to pay is that the OIC is not about free, but the AIC is also not free, right? So my question is, could you give more information about why OIC is better than AIC?
Oh,
Not so theoretical, because I'm not theoretical service. I can't.
Well, I should say OIC is more general than AIC. So in particular, if your downstream optimization problem is to maximize the log likelihood, then you reduce the index.
Okay, it's just only this point.
Yeah.
So OIC.
Yeah. So the spirit is basically AIC. That's why we use the name.
I see. Okay, I got it. Yeah, thank you.
Thank you for the great talk. My question is about the second part, because in the beginning of your talk, I thought you want to advocate the integrated estimation, the third approach. But in the end, I found that maybe if I didn't miss anything, you only say if the model is well specified, we should use the original one. First, estimate the log likelihood, estimate the distribution P, and then perform the DLO. So then when should we use that one? Because even if the model is not well specified, maybe I need to consider the computational efficiency.
Yeah, so indeed. So I have only talked about one result in the second part, and that result is far from being a complete story.
Okay, I see.
So for example, if your model is not that well specified, then pretty much the consensus is you should use IEO because it works better, right? Also, in reality, no model is well specified.
Okay,
it's a myth, right? Like well specification is a myth. So, so you always have a certain degree of specification. So then the next question would be, instead of looking at just this kind of asymptotic result, you should probably get a finite sample that kind of review the trade-off between the amount of the specification and what the
because I haven't worked on exactly the same problem, but I worked on some similar problem, also like bi-level optimization. Then some researchers use influence function to try to I don't know how it's called. It's like a propagate the gradient of the error signal of X into theta. Then using the influence function. Then in order to do so, you need to go through every layer of the entire model of X. Yeah. So if X is a big model like resonant 50, it will be very slow. But if I I suffer from some model miscommunication. I use the ETO, the computational time is fixed. Even if maybe I get some not accurate solution, but if I use the third approach, I don't get a solution within maybe 1 week or some limited time. Maybe computational efficiency is also a point to be considered.
Oh yeah, definitely. So IEO, as I said in the high level common belief, is IEO is better, but it's computational richer.
Oh, okay.
So I think that match what you have.
Okay, yeah. My personal experience is that in many cases, if you want a faster solution, we should still use ETO.
Yeah, exactly. I mean, ETO you could just use off the shelf. It's, it's just a standard estimation problem.
Okay, I see.
Yeah. So that's why we were trying to see.
So you currently you don't have off the shelf toolbox for the IEO.
No, and I think it's very hard because
H is general.
Yes.
I see. Okay, thank you very much.
I mean, H is general, and also X data has to be parameterized, and that computation not sure how to be efficient.
Hello. Yes. Thank you for the talk. I want to ask maybe a general question about operations research. So I guess one of the main challenges is operations itself, right? The logistics. So, for example, in the news vendor problem, you give an example about the constraints of the inventory problem. But in practice, maybe there are many constraints. And maybe for business, the constraints actually change even weekly or monthly. So are there any solutions for that problem?
Well, if the constraint change, then that means your optimization or the mathematical programs.
Right.
Yeah. So, I mean, if the business cycle is like per week, you need to order this inventory. That means essentially at the beginning of each week, you need to resolve an optimization problem. And then if there are a lot of constraints, yes, it might happen. In fact, I'm sure like for, big companies that has a big distribution networks, they have to probably routinely solve this math program. And, there's like basically one of the core part of optimization research is to understand what's the scale that you can solve for different classes of mathematical programs.
Okay, thank you. So maybe a follow-up question, because I think there's a gap between research and business. It's sometimes business people are very skeptical. Do you encounter any case that business people actually don't believe in the results that the model gives?
I think so. Yeah, I think so. My experience with so for instance, for the first project that I presented, right, with the CT agency, right? So you would have to make them understand what are these tools, because different people have different backgrounds and like concepts like optimization or other things like simulation. Even though I perhaps are familiar, I realize not everyone is familiar. So you sort of need to convey to them what can they do, right? Like they can, for example, in optimization, they can find you, the best assignment that satisfy your criterion, and at the same time, there's some trade-off that you want to avoid, and that also could be done, right? So just explain carefully.
Thank you.
Thank you.